I'll begin with a scripture. I'll find it here. This is Philippians chapter 2, verses 14 and 15. It says the following. It says, "Do all things without grumbling or disputing, so that you will prove yourselves to be blameless and innocent, children of God, above reproach, in the midst of a crooked and perverse generation, among whom you appear as lights in the world, holding fast to the word of life, so that in the day of Christ I will have reason to glory, because I did not run in vain or toil in vain." That's from Philippians chapter 2. I don't know about you, but I have trouble doing things without grumbling and complaining, right? I think that's something we all struggle with, right? But anyway, I'll begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for this class and this opportunity we have just to meet together and study your creation. Help us to understand more about limits today, and just help the students to ask good questions as they think of them, Lord. In my prayer, Lord Jesus. Amen. So do you guys have any questions? If not, that's okay. I've got tons of examples. Problem what? 44. Oh, well, we did that the other day. I did that like Monday. We wrote that out. Yeah. Problem 50. I could do something like problem 50. For example, problem 49. So, since there is a request, problem 49 I will do. You're supposed to prove from the epsilon-delta definition of the limit that the limit as x goes to 3 of x squared plus 2x plus 7 is equal to 22. First of all, do we believe that? Is my problem at least reasonable? Okay, so we're supposed to prove from definition of limit. This one's a little trickier than the one I did before. What is, does that at least make sense? What's 9? 9 plus 6 is 15. 15 plus 7 is 22. Yeah, I think this is what it should be. So the question is, how can we establish it directly from the definition? All right, so let me do some scratch work here. So here's scratch. Our goal, ooh, that's not goal. What's that? Goal. Use 0 less than absolute value of x minus 3 less than delta to establish the truth that the absolute value of x squared plus 2x plus 7 minus 22 is less than epsilon. All right, that's our goal. And really what we're trying to do is to find some formula in terms of epsilon to make this true. So let me just kind of focus on this for a bit here, see if we can understand this better. So we've got the absolute value of x squared plus 2x minus 15, right? That's what that is. Something cool happens with all of these problems. Like the factoring you faced on quiz 1 is kind of unguided, right? You don't know what's going to happen. You're like, it's prime, it's not prime, I don't know, right? Some things worked out, some things didn't, 50-50, right? But here, you have, I can tell you there's an expectation with these problems that you will be able to factor this out. Whatever the limit point is, x minus a, that will be a factor in these problems. So, all right, that's the absolute value of x minus 3 times what? X plus 5. Did it work? Was I right? I'm right. Now the properties of absolute value say that that's the absolute value of x minus 3 times the absolute value of x plus 5. Right? Now let's think about this. All right. So this right here we control this, right? We can do what we want with that. That's fine. We can make that as smaller than delta. But the other thing is troublesome. You see? What is the absolute value of x plus 5 equal to in this context? Let's draw a picture. So like, what absolute value of x plus 5 is something like this, right? Where this is a y-intercept of 5, slope 1, right? Y equals x plus 5. So how big is that if x is close to 3? Remember the condition here, what we're looking at is x close to 3. That's where the limit is evaluated. So think about this. We're at 1, 2, 3, right? And so that makes the values of x plus 5 kind of sort of close to where? Oops. Like here-ish, right? That point right there is what? That is 3 comma 3 plus 5, right? 8. That's 3 comma 8. So this is approximately 8 at the limit point, right? All right. So that means that there's hope. But how do you capture that? Well, here's a trick. Here's basically a trick. Suppose you're within plus or minus 1 units of 3, just for the sake of discussion. What would that say? That would say you're from here to here, right? So let me put that in more explicitly. So I'm saying, what if, in fact, the absolute value of x minus 3 is less than 1? What does that equation say? First of all, you should say it's not an equation, you dummy. Hey, that's not polite. Don't call me a dummy. How dare you? You're not my children. You know what's fun at the breakfast table is just go, hey, dummy, and see how many of them look at you. And then they realize what they've done. It's so much fun. My children have started to become averse to responding to hey dummy. They just sit there, staring forward, refusing to look sideways at me. It gives me hope. So this says you're less than distance 1 away from 3. Let's unpack this. Unpacking this, we have minus 1 less than x minus 3 less than 1. Furthermore, that gives us I'm really interested not in x minus 3, though. What am I interested in here? This is what I'm after. I'm trying to make that behave. So what I want to do is add 8 to this inequality. Adding 8 to this inequality gives me 7 less than x plus 5 less than 9. Notice that 7 is greater than minus 9. Seems safe to say. Now, if you focus then on this right here, then from that I learned that the absolute value of x plus 5 is less than 9. If I have the condition that you're no more than 1 unit away from the limit point here. All right? Now that I've explained to you a little bit of my backdrop, let me just here's the proof. Let epsilon be greater than 0 and choose delta equal to the minimum of 1. And apparently I need a epsilon over 9. All right. That's clearly greater than 0. If the absolute value of x, if 0 is less than the absolute value of x minus 3 is less than delta, then x minus 3 is less than epsilon over 9, and the absolute value of x minus 3 is less than 1. Right? Because if delta is the minimum of those two, it has to be smaller than both of them. You guys get that? So this is the way I can impose both things at once. I can have that I'm no more than 1 unit away from the limit point, and I can have that that my delta is no more than epsilon over 9. Okay, so then what? Observe Absolute value of x minus 3 less than 1 implies minus 1 less than x minus 3 less than 1, which implies that, you know, let's see, where was I? 7 is less than x plus 5 is less than 9. Thus, the absolute value of x plus 5 is less than 9. Consider then the absolute value of x squared plus 2x plus 7, all right, minus 22. If it's helpful for you to make a complete connection to the definition of the limit I wrote down, right, I think Monday, wait a minute, no, Tuesday. The secant line equation was Tuesday. Whoever asked me about that, that was Tuesday. We did that about 20 minutes into class. But this right here is what I would have called f of x, and this right here is L, right? F of x minus L. We're trying to show that that is less than epsilon, given the condition that we're within delta units of the limit point. Okay, so basically we're just rehashing our steps here again. This is equal to straight up by algebra x minus 3 times x plus 5, right? Which is, by the way, equal to the product of x minus 3 times x plus 5, all right, which is less than delta times what? 9. But what else do we have about delta? I mean, this right here tells me what? Delta is less than or equal to epsilon over 9, right? So this is less than or equal to epsilon over 9 times 9, also known as epsilon. Hence, the limit as x goes to 3 of x squared plus 2x plus 7 is equal to 22 by definition of limit. And that's the end of it. So this right here is the part I would grade. This over here is scratch work, all right? Like, I think it's important scratch work for you guys to see, because I need to explain to you like where, like if I just wrote down the proof, right? Like I did the other day, it's very mystical. Where on earth is this coming from, right? Okay, but there's a very simple and methodical way it's being arrived at, right? You're just asking the question, okay, so I've got this thing here, x plus 5, and I need to control it. I need to make it not too big, right? And as long as I'm not too far away from the limit point, I know, it's no bigger than 9. Yep.
So in the equation where you put, what was the other one? The other part, there's epsilon and then
Delta?
Delta. You put delta times 9. Did the 9 come from the x plus 5?
Yes, because x plus 5 we just worked out here. So I'm using, so proofs are read top down. So everything I've done before I could use afterwards. So like, keep that in mind as I'm grading. You might be like, but I wrote such and so forth. Well, if you write such and so forth afterwards and not before, like there's causality in my proofreading. Like it has to be top down. We can't, it's not just the equations and inequalities which appear, it's the order in which they appear that matters. So this then is used right there, like you said, yeah. Oh, lest I forget, the ever important attendance sheet. I made a new one, so hopefully all your names are on there. See, it's fresh. I just saw something, so here, I'll tell you my own personal experience. Is like the first time I ever saw this, I just saw somebody do it. They didn't explain where the delta minimum of one thing is coming from. Like, why are we doing that? no one explained to me, and so I'm just like, what? Why? What's that? What's going on? There is a simple idea behind it. And if you understand this carefully, you could actually adapt this method to many other examples, which I won't actually test you on. I'm going to test you on 3 things, right? This kind of example, the linear example I did Tuesday, and possibly like the proof we went over the other day about the sum of the limits being the limit of the sum. So I asked Dr. Sprano, I'm like, do you test on that? He's like, oh yeah, I put that on test 1. I'm like, okay. I want to make sure I'm not harder than Dr. Sprano. If I'm harder than Dr. Sprano, I've done something wrong. This Dr. Sprano's pretty tough. Anyway, in a good way. All right, so let's see here. Let's go on. Are there any questions? Next question, let's say. All right, so let me just throw out some fun facts for you guys. And maybe we'll prove some of these more in the future, but let me just put them on the table here for us to use. For example, the limit as x goes to a of e to the x is equal to e to the a. The limit as x goes to a of, instead of x goes to a, let me say x goes to x naught for a change. A to the x is equal to a to the x naught for, a in the reals. Well, I probably should say for a greater than 0. All right. Let's make sure we have a positive base. I think, yeah. Negative base, troublesome. Let's see, what other functions do you guys care about? How about this? Like the limit as x goes to a of the nth root of x is equal to, well, the nth root of a. And here we're going to assume a is greater than or equal to 0. Right? And then, so a is greater than or equal to 0 if n even, and a is a real number for n odd. We can take the cube root of a negative number, the 5th root of a negative number, that's fine. But the 5th root of the 4th root of a negative number would be like imaginary. Okay, so we probably shouldn't do that. We try to keep it real in here, right? What else? Any other functions you guys like? How about sine and cosine? How do you think those work out? Like limit as theta goes to theta naught of sine theta. What do you think it is equal to? So surprisingly, sine theta naught, cosine theta naught. Right? Example 2. How about tangent? If you know this, can you figure out tangent? What would be the limit as theta goes to, say, theta naught of tangent theta? How would that work out? Okay, yeah, you're saying that's actually sine theta over cosine theta. And so we can say that that's the limit as theta goes to theta naught of sine theta divided by the limit as theta goes to theta naught of cosine theta. You see, so if we know the limits of sine and cosine, we get the limit of tangent just the same, right? Because we have a limit law for quotients, right? Limit of a quotient is the quotient of limits, although there's strings attached here, isn't there? What's the deal? So that's tangent theta naught, right? Provided what? This step right here is only legit if what? Cosine theta naught is not equal to what? 0, right. Where is cosine theta naught equal to 0? Let's draw a graph. What's tangent look like? So remember, cosine is 0 where? At plus or minus pi over 2, plus or minus 3 pi over 2, right? Odd integer half multiples of pi. So these are the places where you've got division by 0 for your tangent, and those are the places where this limit, of course, does not exist. So the graph of tangent looks something like this, right? Sorry, I think my intervals have gotten squished as you get further. Like my theta axis is kind of like compressing as you go away from the origin, my bad. But anyway, so the limit does not exist if theta naught is like plus or minus pi over 2 or plus or minus, right, 3 pi over 2, so forth. Does that make sense? You guys tell me, what would, if I was to ask you this, what's the limit as, say, theta goes to pi over 2 from the left of tangent theta? What would that be equal to? What would the limit as theta goes to pi over 2 from the right of tangent theta be equal to? So let me demystify this. This minus means you're looking at values a little bit negative to the limit point, these guys. So this one is infinity. On the other hand, the other guy, you're approaching for values a little bit bigger than pi over 2, these guys, and those give you minus infinity. All right? What's the double-sided limit at pi over 2? It does not exist because we get minus infinity from one side and infinity from the other. All right. Example 3. What if we're up against the limit as x goes to the natural log of, 8 of hyperbolic sine of, let's say, 3x? Can we do this? How does this work out? You guys are like, I don't know what hyperbolic sine is. Well, I know that. That's why I'm doing this example. All right? So reminder, hyperbolic sine is a new function that we defined. So like sinh of theta is 1/2 e to the theta minus e to the minus theta. In contrast, the hyperbolic cosine of theta is 1/2 e to the theta plus e to the minus theta. Right? These are hyperbolic sine and hyperbolic cosine. They're just particular combinations of the exponential and exponential with a negative argument. They're respectively the odd and the even parts of the exponential. Cosh plus sinh is the exponential. Okay, anyway, so here, this is what? This is actually what? Limit as x goes to the natural log of 8 of what? You got yourself a 1/2 e to the 3x minus e to the minus 3x, right? That's what this means. Let's work out the limit using limit laws. And I'm not going to write all the limit laws out. I'm just going to like try to do as many of them at once as I can just to kind of get to the point here. So what this is 1/2 the limit as x goes to log 8 of e to the 3x minus 1/2 the limit as x goes to the log of 8 e to the minus 3x. So you can, the limit of a sum is the sum of the limits. We can pull the minus 1/2 out. Getting to the point here, since the exponential has a limit which exists everywhere, all right, you could just plug in the limit point and work it out. Like, long story short, this is straight up equal to 1/2 e to the 3 natural log of 8 minus 1/2 e to the minus 3 natural log of 8. I'm technically using the composite limit law, which says that the limit of a composite function is the outside function evaluated at the limit of the inside function, provided the outside function's nice. But anyway, so like, let me just try to say it in more simple words. if you can plug the limit point into the expression, and if you can do that in the sense that when you plug it in, you get an expression which is not ill-defined, which doesn't have a division by 0 or some other kind of, violation of arithmetic, then you can just do that, right? That's ultimately the point of my whole discussion of limits is, at the end of the day, as long as the expression is nice at the limit point, you can just plug the limit point in and it gives you the limiting value. We can do better here though. Can you guys tell me how to simplify this? We'd like to write this number not in this way, but in a better way, in terms of just like square roots or something like that. So let me show you how this goes. So remember the properties of log? Like p times the natural log of stuff is equal to the natural log of stuff to the p, the power property. So you see that log of 8 to the 3 log 8 is actually 1/2 e to the log of 8 to the 3rd power. And then you've got minus 1/2 e to the log of 8 to the minus 3 power, right? Now remember, e to the natural log of positive stuff, or say positive whatever, is equal to positive whatever. That's an identity for the exponential and the log. They're inverse functions. This is the very nature of the construction of the natural log, to be an inverse function to the exponential. And so with that, we just have what? We have 1/2 8 to the 3rd power, right? Minus 1/2 8 to the minus 3rd power, which we could rewrite as 1/2 8 to the 3rd minus 1 over 8 to the 3rd. So there you go. That's actually what this is equal to. And of course, we could simplify that further if you're so inclined. Do you want me to? Do you feel better about your day if I simplified that? Maybe, slightly? Let's see here. So you should have seen these kind of simplifications before, but hey, maybe it's been a minute since you did them, so I thought it would be good for us to do it again, yeah? Oh man. Oh, rats. It is, my calculator is, it usually, it's not behaving. This may be beyond the, goodness, my calculator cannot hack it. I am surprised. I did not think this would be a nasty enough fraction that the calculator couldn't do it, but it's choking. So, oh well. If you want me to, I could do it by hand, I guess. There's a common denominator. Maybe we'll figure out why the calculator can't do it. I'm kind of curious. So this is 1/2. Common denominator here of 8 cubed, right? Oh, I start to see why. 8 to the 6th. Okay, I see. 8 to the 6th over 8 cubed. Yeah. All right. I guess I can. I'm gonna take it easy on my calculator because I'm just asking it to make a distinction between 8 to the 6th and 1. Like I'm subtracting just 1 off 8 to the 6th. How big is 8 to the 6th? Yeah, it's big. So it's beyond the, anyway. If you want to know the exact fraction, we'll have to use Wolfram alpha or something. So.
And 127.
Well, I mean, I could simplify it further, but anyway, let's go on. All right, so let me do some more here. All right, so I just want to go through a sort of a lightning round of easy examples where we can just plug in the limit point, all right? And maybe there's no problem, and then we'll get snagged on one where there actually is a problem. So let's do some just easy routine problems, because these are something that we come across. They're not all complicated. All right, so but I should talk to you guys about how we deal with like composition. So example 4. What if we had like the limit as x goes to 7 of, say, cosine of pi x? How would that go? Or how about limit as x goes to 1 of like the cube root of 3 plus 1 over 1 plus x squared? Or how about like the limit as x goes to infinity of x to the 6th minus x plus 1? Or what if we were up against something like the limit as x goes to minus infinity of like 3 plus e to the x? There, we'll chew on these 4 examples here for a minute and see what we can do. Okay, so the first one is what? We just do what? Cosine of? Yeah, cosine of 7 pi. What is that equal to? That is equal to minus 1. Right? So we shouldn't leave cosine of 7 pi as our answer. The answer is minus 1. I do expect that you simplify cosine of 2 pi or cosine of 3 pi, things like this. You should know to use elementary trigonometry to simplify them, right? So that's part of this. How about this one? Now, would I give you a lot of partial credit for cosine of 7 pi? Absolutely. All right, but I do want you to simplify. How about this one here? Cube root, so what do you do? I could just plug in the number, right? So I get the cube root of 3 plus 1 over 1 plus 1. Yay. Yeah, 1/2. So what's 3 plus 1/2? It's 6 halves plus 1/2. 7 halves, yeah. So there you go. You got the cube root of 7 over 2. That's good enough for me. All right. How about this one? X goes to infinity of x to the 6th. What's the rule for limits at plus or minus infinity for a polynomial? What wins? It's the largest power, right? When you're really, really large, whatever's the highest power is going to be dominant, right? If you're at 1,000, you've got 1,000 to the 6th power versus x just being 1,000. So yeah, you're subtracting 1,000, but you're adding 1,000 to the 6th power. The 1,000 to the 6th power totally, it wins, right? So the answer here is infinity, because this function grows without bound as we go to infinity. How about this one? What happens as x goes to minus infinity of 3 plus e to the x? If I had to graph this, it's got this 3 right here, right? This function starts, it goes through the y-axis at 4, right? Because f of 0, this 3 plus e to the 0 is 4, so it's going here, and the function looks something like these. So if you know how to graph, great. You should be able to see the answer from the graph. What's the answer? 3. Now suppose you don't graph it. Is there another way to do this? Sure, you don't have to graph it, right? You can think about what happens to e to the x as x goes to minus infinity. That's just like 1 over e to some really large positive quantity, right? So that's becoming very, very small as x goes to minus infinity. So a couple of things to keep in your toolbox are these. Limit as x goes to infinity of like a to the x is equal to infinity. The limit as x goes to minus infinity of a to the x is 0, right? These are These are nice to remember. Now there's some context here. We're assuming that a is greater than 1, right? Why does that matter? How about this one? What if I have like limit as x goes to infinity of, say 1/2 to the x plus 3 power? How would that go? What does that mean? X goes to infinity, 1/2 to the x plus 3. Think about it. You're basically taking 1/2 times 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 1/2 forever and ever, amen. That's really small, So this is exactly 1/8 the limit as x goes to infinity of, well, really it's 2 to the minus x. You could look at it that way, right? So corollaries to this, the limit as x goes to infinity of like a to the minus x is equal to the limit as x goes to infinity of 1 over a to the x. That's 0. On the flip side, the limit as x goes to minus infinity of a to the minus x is equal to the limit as x goes to minus infinity of a to the x. Wait a minute, what? Oh, I just did the same thing twice. That's dumb. Let's try this again. A to the x. Oh, I forgot to think. I'm sorry. Let me stop this. I thought there was something to say here. I'm just being dumb. My bad. Anyway, the point of this is just that this up here is what? It's 0, all right? All right. Let's look at one which is not so obvious, all right? And I think I have this problem in the homework I assigned you guys, so it's probably, just the friendly thing to talk to you guys about it. So let's do it. What about inverse? No, not inverse. Just hyperbolic. What's hyperbolic tangent? What if I was to ask you, example 9, what's the limit as x goes to infinity of the hyperbolic tangent of x? So first of all, let's talk about what that even means. What is hyperbolic tangent? So by definition, this is sinh x over cos x. That's the definition of the hyperbolic tangent. Just like tangent is sine over cosine, hyperbolic tangent is hyperbolic sine over hyperbolic cosine. But think about what that means in terms of exponentials, right? So like, what is that? That's 1/2 e to the x minus e to the minus x divided by 1/2 e to the x plus e to the minus x, right? So do we need the halves? No, we really don't. So what are you looking at? You're looking at a ratio of a sum and difference of exponential functions, all right? And so we ought to be able to understand how this thing behaves in terms of the ones I was just writing on the leftmost board, right? Just like the fact e to the x goes to 0 as x goes to minus infinity, all that stuff, right? I want to show you there's 2 formulas I think about to understand hyperbolic tangent in the long run. And here they are. Okay, so I've got, first of all, forget about the half. We got e to the x minus e to the minus x and e to the x plus e to the minus x, right? Okay, so how can we simplify this formula? How about this? Can you factor exponential? Can you factor e to the x out of both the numerator and the denominator? Let me say it a different way. What happens if you divide this fraction, both the top and the bottom, by e to the x? Let me say it a different way. Suppose you multiply the numerator and the denominator both by e to the minus x. What happens? Let me take that tact. Multiply by e to the minus x. What happens? Can I multiply it by e to the minus x over e to the minus x? I certainly can. That's just the number 1, right? Is e to the minus x ever 0? Search your heart. It is not. So when I multiply, what happens? I get, e to the x times e to the minus x minus e to the minus x, e to the minus x. Downstairs, I get e to the x, e to the minus x, plus e to the minus x, e to the minus x. How does that simplify? What is that? Well, e to the x and e to the minus x, what is that? That's just 1, right? So I get 1 minus e to the minus 2x divided by 1 plus e to the minus 2x. And how does that formula help me? Think about it, right? What's the limit as x goes to infinity of hyperbolic tangent of x? Well, it's the same as calculating the limit. I mean, this is just straight up an algebraic identity. 1 minus e to the minus 2x over 1 plus e to the minus 2x, right? What happens as x goes to infinity of e to the minus 2x? A notation I like for this kind of problem is to just use like an arrow to say, this goes to 0, that goes to 0 in this limit. And so the answer is 1. The answer is just 1. Because it's 1 minus 0 over 1 plus 0, also known as 1. The limit is 1. All right? Now, okay, so what if I was to ask you the limit as x goes to minus infinity? How would that work out? So check this out. You can also write hyperbolic tangent of x through a very similar algebra problem. Instead of multiplying by e to the minus x over e to the minus x, if we simply multiply by e to the x over e to the x, then the e to the minus x's will cancel. By almost the same algebra, we will get e to the 2x minus 1 over e to the 2x plus 1. This is also an identity which is true for the hyperbolic tangent. What happens then in the limit as x goes to minus infinity for hyperbolic tangent? That was supposed to be a minus infinity. I lost my minus. Oopsie. What's the big difference? Plus infinity, minus infinity is all. No, it's not all the same. Very different. Pretty diametrically opposed. Right. Do you ever think that one of Superman's special powers is not letting people know that he's Superman when he's not wearing his outfit? Like, has he got some sort of like telekinesis that's not letting people see that he's obviously the same dude? Because there's no mask, right? I was thinking about this. What do you think? You're like, I don't. Oh. So it's just, we see what we're expecting to see? Ah.
I don't really think Superman's going to be in this room, so.
I guess the life lesson is when you're doing your homework, you should be expecting to see the answers so that way you might see it, you know? That's where I was going with the story the whole time. But anyway, so that's a good answer. I like it. So x goes to minus infinity. What happens now? Well, these guys are super tiny in that regime. And so what do you got? 0 minus 1. Oh, man. Is that minus a minus? Come on. Seriously? Dude. Plus. So 0 minus 1 over 0 plus 1, also known as minus 1. So something I don't think I've said in class yet, but I should, is that limits give us a precise way of encapsulating ideas that you've seen in pre-calculus. Like we talk about horizontal asymptotes of functions, right? So if the limit as x goes to infinity or the limit as x goes to minus infinity exists for a function, that means that the function has a horizontal asymptote of that value. So these calculations we just did show that the hyperbolic tangent has two horizontal asymptotes, one at 1 going to infinity and one at minus 1 going to minus infinity. And the graph of the hyperbolic tangent, it look something kind of, sort of like this. There you go. That's the hyperbolic tangent. Kind of boring in some sense. It is somewhat reminiscent of the inverse hyperbolic, excuse me, it's somewhat reminiscent of the inverse tangents graph. Inverse tangent, on the other hand, goes to plus or minus pi over 2, and it's just the graph of tangent flipped sideways, the thing I just erased. Yeah. So, do you guys know what the graph of, like, what if I asked you, here's an easy one. Well, ostensibly an easy one. Example 10, what's the limit as x goes to infinity of like cosh x? So we're talking about what's the limit as x goes to infinity of 1/2 e to the x plus e to the minus x, right? How's that go? Well, e to the minus x, that's super tiny. So this thing goes to 0. That, on the other hand, goes to infinity. So what's the answer? Infinity, right? So this thing blows up. So for your reference, guys, the graph of hyperbolic tangent looks something like this. The graph of hyperbolic sine looks something like that. I think I've said this in a previous lecture, but you know, I say a lot of things, so it bears repeating. So there's the graph of cosh, there's the graph of sinh. The limit as x goes to infinity of both cosh and sinh is infinity. The limit as x goes to minus infinity of sinh is minus infinity. Of cosh, it's infinity. Cosh is always larger than 1. Its smallest it ever is 1 when it crosses the y-axis, right? And don't be deceived. These are all, these side things here, these are exponential growth, all right? So, okay, let's move on here. I need to look at things that are more tricky. Tricky. Still got time, we're good. Okay, so the things I've been belaboring so far, these are the basic things that we essentially just plug in the limit point, and that's kind of it. What's more tricky is when we have indeterminate type. What are the indeterminate types? So I give you a list of the basic indeterminate types on page 61 of my notes. I'll write them out here because we should make sure we know them. Lim f over g is of type 0 over 0, right? That's true only if lim f equals to 0 and lim g equals to 0. Lim f over g is of type infinity over infinity. That means that the limit of f is infinity and the limit of g is infinity. All right. And let's see here. Limit of f times g is of type 0 times infinity. If and only if we've got like limit of f equals to 0 and limit of g equals to infinity. limit, there's 4 of them, f minus g is type infinity minus infinity if, guess what? You've got the limit of f is infinity and the limit of g is infinity. So these, my friends, are the basic indeterminate types or forms. All right? And what it means whenever you find a limit that has this pattern, it means we can't be sure what the outcome is at first glance. All right? For instance, we've actually worked one of these today. I just didn't sell it to you very much, in some sense, right? Like the hyperbolic tangent example, right? Think about that one. If we look at the hyperbolic tangent example as sinh over cosh, what's the deal? What's the limit of sinh over cosh? Well, let me just recap here. Example, where am I? Example 11. So I'm just going to recap this one here. So if you look at the limit, x goes to infinity of like sinh x over cosh x. This right here is type infinity over infinity. Why is that? Because as I was just explaining to you guys, the limit as x goes to infinity of cosh is infinity. The limit as x goes to infinity of sinh is infinity. So it's not really clear at the start which one's going to win. However, the algebra step we did of simply multiplying the top and the bottom by e to the x, right? Trading this expression for this one, 1 minus e to the minus 2x over 1 plus e to the minus 2x, right? Then that's just straight up 1 minus 0 over 1 plus 0, which was equal to 1. So what removed the indeterminate form was the algebra we did on the middle board. All right? So something had to happen. We had to multiply. You see, we had to multiply by e to the minus x over e to the minus x to see that. At least I did. Let's look at another one, which is a little bit less... that's kind of a quirky example to start you guys with. We actually did one of these the other day. But let's do another. Let's see if I can come up with a good good one here. What if we're up against... Let me try to find something that's kind of similar to one of the ones I've assigned you guys. Give me a second to remind myself. All right. All right, I'll try to do K from problem 80. All right, so by the way, a lot of the starting ones in problem 80, you could just do the way we were doing start a class. Probably just plug it in. All right, here we go. Limit as t goes to minus 2 of y squared plus 9y plus 8 divided by 2y squared minus 128. Wait a minute. Sorry guys, I copied that down wrong. my eyes keep jumping from one letter to the next. Like, be careful with this when you're doing your homework, right? You don't want to solve half of one letter and half of another. Like, that's not the assigned problem, right? Don't do that. Don't be like me right now. Y goes to minus 8, y squared, 9y, 8, 2y squared, minus 120. All right, there we go. Now I've actually got the problem. So what is the first thing you do with any limit problem? You try to do what we did at the start of class. You try to just plug in the limit point. If it works, wonderful. You're done. If it doesn't, well, then you got to do algebra. All right? Be careful not to write something illogical like it's equal to 0 over 0. That wouldn't be true, right? So you want to kind of go off to the side here and actually plug in the number. What happens if we do that? So if I put y equals to minus 8, I get what? Minus 8 squared plus 9 times minus 8 plus 8, which is equal to what? That's 64 plus 8, which is 72. 72 minus 72 is 0. Aha! And what's 2y squared? So 2 times minus 8 squared minus 128 is what? 2 times 64, which is 128. 128 minus 128, 0. Aha! I have now earned the right to write under this. Type 0 over 0. You're rats. So I can't just plug the number in because 0 over 0 is not a thing. What I can do is I can factor. Factor theorem says what? If you have a 0 for your polynomial, there's a factor corresponding to that 0. So what do we know about factoring these expressions? What can we factor out? Don't work in the dark. Work in the, at what? A y plus 8? Yeah, y plus 8. Y minus 8 is a good, almost right guess. But y plus 8, because factor theorem, remember, says f of c equals to 0 if and only if, like, in this context, y minus c is factor, since we're working in the variable y, right? Factor theorem. So since 8, when we plug in minus 8 rather, we get 0, that means that y plus 8 must be a factor. So there has to be a y plus 8 upstairs, and there has to be a y plus 8 downstairs. I'm going to pull the 2 out. Well, no, fine, I won't. I'll just leave it. I'll just leave it, except this is the difference of squares. Actually, let me not be dumb. Let me not be dumb. This is the difference of squares. We can factor that. So what this is square root of 2y plus the square root of 128 square root of 2y minus the square root of 128. Difference of squares, that's how that factors. Actually, ooh, this one's kind of, it's kind of nefarious in that regard. Man. So this, oh, look at that. You see what that is?
Why do you want to do the square? Don't you want to just factor out a 2 from that whole equation and then just do y plus 8, y minus 8? Yeah.
You could do that.
Okay.
Sure. I will give the people what they want. 2 times y plus 8 times y minus 8. There you go. Feel better? Okay, cool. Sorry, sometimes I have a... Anyway. What I was doing was not wrong, it just also wasn't right. So anyway, so y plus 8, how do we factor that? What's left? Oh, y plus 1, right. You're not factoring in the dark is my point with these. Once you know it's type 0 over 0, you know what you're factoring out, right? You can do it. In some sense, the factoring I asked you in quiz 1 was much more difficult, right? Because there was no limit to guide you. The y plus 8 and the y plus 8, they'd be canceling, right? Why is that okay? It's okay because y is not actually equal to minus 8 in the limiting process, baked into the cake of the definition. So those cancel out. And what we got? We got ourselves a y plus 1 over 2 times y minus 8. All right, and then what? Plug in the minus 8. So we've got minus 8